Howdy, everybody, and welcome. I hope my audio is coming in clearly. I believe I've tested it all, but you never really know with some of these things. I'm going to try recording some of our lectures a priori. I'm also going to try and record some of the reading of the textbook to help complement some of those pieces if you're studying alone outside of class. The idea is that we can have these to watch pre-lecture / pre-class session, I should really say, so that our class sections can be a lot more interactive, geared towards practice, asking questions about things that didn't make sense. It'll give you the opportunity to do things that are accessible to you. Like, I don't know if you're like me, I like to watch things on double speed and pause and rewind kinds of things, hit multiple times and separate that out, sometimes in close repetition, sometimes in far repetition. You're like, I revisited this lecture. Let's do it a week from now when I have heard some other things and see how some of these things kind of layer on top of each other. So hoping to do that, that my shadow clones that I make for you will be able to help you out. That's sort of the intent of these ideas. So without any further ado, for the first one, what I want to talk about as our way of getting started with electricity and magnetism is kind of just laying out all of the topics that we're going to go through and do a quick little chat about some of these pieces, what I'm going to go through. So the first thing that we're really going to need to get into is talking about charges and what are charges. What do we mean when we say that things have charge? It's this new property, or new to maybe a few of us. Typically, if we've taken any kind of chemistry, the high school physics, biology, we've heard about these things called charges. And typically we come in with foreknowledge about, there being two types. There's these positive charges and these negative charges. There's a newish idea that we'll get into about quantization, where there's this smallest unit that you can break these down into. In our cash, if you're dealing with cash, a penny is sort of the smallest unit. Yes, theoretically you could have something smaller than a penny, but in physics, in this idea of electricity and magnetism, the smallest unit of charge that you can have is plus or minus this one amount of charge, whether it's a positive charge or a negative charge. So a proton has a charge of plus 1.602 times 10 to the negative 19th of these units we call coulombs. We'll talk about this person with the last name Coulomb, where that name comes from. But this is getting that idea that 1 coulomb is an absolutely enormous amount of charge. We'll talk more about those things. And in order for things to have no charge, you have to have some sort of combination of these two pieces. And, that's also to say, there's technically these things called neutrons, which have 0 charge. So we've got our neutrons, we've got protons, and we've got electrons. And as far as this class goes, these are the only, fundamental particles that exist. Now, yes, technically there are these things called quarks that have thirds or 2/3 charges, and they have to be in combos of 3 at any given time in some particular combination in order to make one of these things. We won't really talk about that because we have to go through a lot of this physics and, learn an additional 150 years of physics to get to that point where we're ready to talk about quarks. So in the scope of this class, this is kind of all there is. And we'll talk about properties of macroscopic objects that are built out of these charges, things that we call and classify as conductors, things that we call and classify as insulators. I was going to say inductor, but I screwed up. I got ahead of myself. Those are something entirely different. But we will also talk about ways that you can charge objects, which gets into conduction, which is pretty related to conductors. There's also this thing called triboelectric charging. And this is basically, you have socks on a carpet, you're rubbing them on, and then you shock a doorknob or you shock your sibling, kind of a thing. That static electricity is typically how that static electricity gets generated is what we call triboelectric charging. There's also charge by conduction, which is kind of that post process, right? If you've charged something triboelectrically, you could then say, let's say I have this conductor that has a bunch of positive charges on it, and I bring it near this other conductor that has no charges on it, if I bring these things together so that I can have them, still learning some of my shortcuts here. If I bring these together and have them bonk and touch, when they do that touch process, assuming these two are exactly identical, they're going to kind of have half this charge split. And we'll learn some of the mathematical rules for how much and how these charges get distributed, because really what we're going to learn in one of these properties of a conductor, I'll say it now and we'll touch on it more why later, it's going to redistribute all of that charge. So I'm trying to draw the same amount of charge, but smaller plus symbols, so that it's still, like, let's say I had 4Q total at the beginning. Now it's 2Q and 2Q distributed. Also for reasons, Q, capital Q or lowercase q, depending on context, tends to be the letters, the algebraic symbols that we reserve for charge. I don't really know why, just we do. So I would say, like, the units of charge are coulombs. Great. And later when we get to capacitance, like, the units of capacitance are going to be this thing that we call farads. There's going to be weird units, weirdly named units, weirdly sized and scaled units that are going to take us time to get used to, which is why I want to have sort of this broad overview of everything that's kind of fast first, and we'll re-dive into all of these things in deeper detail later. So we have those few ways of charging, triboelectric charging, this charging by conduction process, which is typically done between conductors, but doesn't have to be. Conduction. And then there's also this charging process called charging by induction. And you basically induce another charge. So basically the idea is, if I have maybe this thing of 4Q over here, and I've got this neutral conductor over here, if I connect a wire over to this so-called ground, we'll talk about ground and different ground circuits when we get to circuits, and the different symbols that we use and why we call them ground, those sorts of things. But the idea is, if I do a particular process where I bring this thing close, but don't touch it, so there's not conduction happening, it's going to polarize this material. So it's going to pull negatives in here, which leaves behind positives, but those positives kind of have this avenue to go towards this ground. So if I then take my little scissors and I go, bye-bye, now if I can take this away, and it's still... I see what happened. Okay, I can take it away now. And this thing will redistribute its charges in this way to be uniformly distributed over the conductor. That's what's going to be this thing that we call charging by induction. We'll talk more about that. This is just a very quick overview. And again, that thing that I highlighted here, that redistribution of charges, that's really the property that marks the difference between conductors and insulators. Where conductors, they have these free charges on them, and so the charges are free to move if there's a reason for them to move. And the reason in this case is that negative charges don't like being near other negative charges. They repel like kinds. That's sort of the opposites attract, likes repel kind of idea here. So these negatives, they don't want to be near their other negative friends. Positives don't want to be near their other positive friends, and so they repel, and they redistribute themselves across eventually the surface of the conductor. We'll explain why eventually, why they aren't in the middle of the conductor and they're only distributed across the surface. But that's sort of the idea here with our basic properties of charges and things that go into that. I have in my notes here to also talk about conservation quantities. This idea of charge is never created nor destroyed. We can slosh things around, but never create or destroy them. And similar ways that we talked about with momentum and energy. So we have this additional thing, and mass even. These things that are typically conserved. And again, those have asterisks when you get into like very modern physics, but right now for the for what we're talking about in classical electromagnetism, and really we're talking about so-called electrostatics right now, and eventually we'll get into magnetostatics, and at the very, 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 very end, we'll talk about very simple so-called electrodynamics. So we're talking about things that are stationary or quasi-static. They're happening in a very stable and controlled way in non-relativistic reference frames. So we're not talking about like special and general relativity kinds of things in the same way that we did back in Phys1, where we know Newtonian mechanics is not a complete and proper description of the universe. In an interesting way, these things are still going to be true. There's going to be phenomenon we don't talk about, but electromagnetism is actually the thing that led us to figure out special relativity. It's kind of begging for special relativity in particular to be found. And so it's still sort of manifestly consistent with those stronger rules, but there's still going to be some assumptions that we make. And I'll try and be transparent about when and where those are and how, if we continue studying physics, we'll kind of overturn some of these pieces. But for the most part, Phys2 is actually a lot more quote-unquote true than Phys1 was, where we're lying through our teeth all the time when we say things like gravity is a force. Gravity is not a force, it's the curvature of space-time, all these kinds of things. We'll still use some of those things because they're useful for our study, they're useful for our practice and for our learning. And eventually, if you study physics long enough, you'll learn the quote-unquote better/truer ways of modeling these pieces. And even then, when we look at those rules as we built them, they still don't seem to model all things all the time in all cases. And this is an ongoing area of study in science where we're trying to understand how the universe around us works. We still don't have it figured out. So that's a reason to keep looking. Okay. So after we talk about some of these properties of charges, we want to say, let's use these charges and things. Let's explore some of these pieces. And this is where I come up with the phrase that Phys2 is just Phys1 with new sources of forces. Before, we had things like normal forces, we had things like tensions, we had things like frictions, we had things like gravity. And now we're just adding in, right now, one new force. We're going to add in a so-called electric force. And this electric force is very similar to the gravitational force that we dealt with before, where we said this gravitational force is really just equal to some mass. So if I say, for instance, the gravitational force that mass 2 exerts on to mass 1, I would place mass 1 into the gravitational field made by mass 2. And we had this idea that that gravitational field was created by this thing that looks like a constant times that mass divided by the distance between them squared. So the distance between 1 and 2, we squared whatever that distance was. But if this is a vector, we had to make this a vector. So we created this so-called r hat vector, and we said this negative means that it points towards them. So if this r hat vector is defined as it points from 2 towards 1, then the r vector here, the gravitational field, is going to point towards the particle 2. So if I draw that picture out, here's particle 2, here's particle 1. This r hat vector points in this direction, but it's been renormalized to have a length of 1. That's sort of that property of the unit vector here. And so then the final force is going to be based on this gravitational field vector, again, multiplied by whatever mass this is. And so if you write this out in a longer form, you could be like, it's m1 times m2 divided by whatever this r vector is, our magnitude of the r vector squared, times this r hat, times this negative. And again, I'm being fast and loose with some of these notations here, because it's sort of like, what these vectors are based on the picture, based on the context and the geometry of the situation, how things are configured in that space. But the big idea here is that we abstract this into, hey, it could be made by anything else too. If it were multiple objects, I'd have to figure out the net composite gravitational influence of many things, but then I would just multiply in this last piece. This is the idea that we'd really exploit here in electromagnetism, where the electric force looks almost exactly the same. We're going to say it's equal to, in this case, Q1, this being a charge. So I'm going to place a charge at some spot here. And that charge is able to feel a force that interacts with this through this electric field made by the other charge. So if 2 makes an electric field, it's going to make an electric field, if it's positive, away from it. This is the E field made by 2. So then if I place Q1 inside of that E electric field, I just multiply those two together, and immediately I get this thing called the electric force. And it looks exactly the same as this algebraically, where you have a constant. In this case, we call this the Coulomb constant instead of the gravitation constant. Coulomb, that's an M constant. And I always forget the units. We'll rederive them here in a second. But it's 8.99 times 10 to the 9th in SI units. Well, again, we'll figure out what those units are in a second. Multiplied by this Q1. And then this E field, the E field made by an electric charge, as we'll eventually prove here, is going to be equal to that charge divided by this R squared times this so-called R hat thing. And again, this R hat is specifically the R hat if you start at 2 going towards 1. It's the charge 2 is having the role of creating the electric field on Q1. And then Q1 is placed inside that electric field, and that feels the force. If you want the third law pair of that, all you have to do is flip-flop all of those things, where you would say the third law pair of this force would be K times Q2, and then Q1 is going to be the thing that's making the field. So you're going to end up using the same distance between them. This is a scalar. The magnitude of the R vector in the denominator is just the distance between them. We'll talk more about sort of the vector formalities and different decisions we do that when we go into this in full depth. But that's how we're going to be able to calculate the forces on these pieces and their third law pairs and all those kinds of things. And the really cool part about this is when we separate this from forces and fields, we can now talk about the field itself. And so I can now go forward and say, what if I had just a bunch of charges? What if I had one charge that I eventually want to put here, but I've got charge 2 and 3 and 4 and 5, and they're all lined up, and there's a whole bunch more of them that I'm not even going to count. And they're all in this kind of line, this rod, shall we say. And I want to know, what's the total electric force that this rod exerts on this point? Because, we have point charges in the universe, that's great. But we also have a lot more than just single point charges, these things that we need to talk. And so we have to talk about how do all of these pieces interact together. And that's where we can say, well, if I want to create the net E field by this distribution of charges, depending on how that distribution is created, I have some options. If I have just a bunch of charges, like 2, 3, 4, I can do like Q2 over its R squared times its own R hat. And I can add that with Q3 over its own R value squared, because they're going to have different distances between them, as different distance from the source to the point of interest that they're actually having an effect on. And they're also going to have different angles, different directions of this vector. And I could keep doing this for all of these things, which if we've taken any sort of Calc 2, which again, I know Calc 2 is a co-requisite for this class, but hopefully we've seen some of this series kinds of stuff where we're really just saying, instead of labeling these charges one at a time, let's label them in a way that tells us how to label all of them. I'm going to take each charge, so Q subscript I, divided by its corresponding R vector magnitude, its distance away from the target squared. That's what the I is saying. So I'm adding up over all of these until I get to however many total there are. And then I would have to find an individual R vector for it as well, or R hat. And because finding unit vectors is kind of a pain in the butt, what we'll often do is multiply by R over R, so that this just becomes the R vector in the numerator when you take the R hat times the magnitude of R that was in the numerator here. And then I can combine terms here to make it an R cubed. The reason why we don't often like to do that for the first piece is it hides the so-called inverse square law, where it scales as 1 over R squared in terms of strength, in terms of magnitude. But we'll get into that more and more detail as we get into practice, I'm trying to give a big, broad overview of just the different kind of possibilities. So I'm going to leave it back in the original form. And this works great if I have a countable number of charges that I can iterate through. But if I have so many charges, just this uncountably infinite number of charges that are so smoothly distributed, we have to find another strategy. And that's really getting into this idea of discrete versus continuous. I still need to add up things, but when you add up things that are continuous, you end up adding up every small piece of that source. So this time it's DQs divided by their corresponding R squareds times their corresponding R hats. And otherwise it's the exact same thing. We're still adding up each charge divided by how far away it is, squared, multiplied by that direction piece. The weird parts come in here when you're trying to get into bounds, and we'll talk about that when we get into this, but basically what we have to do is break up this small piece of charge into a geometric size, a DL, a small piece of length, and then to make the units work, you have to multiply by some sort of charge density. And depending on what dimension you're working in, like if I had a area, I'd have to break it up into a small piece of area, which means I'd have to multiply by a different type of charge density. And if I had a volumetric shape over which the charges were distributed, I'd have to have an even different kind of density. So these three charge densities, the lambda, sigma, and rhos, are like a 1D, 2D, and 3D density. So like a coulomb per meter squared, and a coulomb per meter cubed as the units of lambda, the units of sigma, or the units of rho. And we'll talk way more about all of those pieces going forward. Trying to give just a very brief shotgun high satellite overview of all these pieces. But again, why we cared about finding these E fields in the first place is because now if I know that E field, all I have to do is multiply by Q1, and I immediately know what the force on Q1 is by this whole whatever huge distribution of charges. I now have the Phys1 quantity I actually care about. Similarly, we're going to introduce another new field quantity. So that was an electric field. We're also going to introduce this thing called a voltage field. And the biggest difference between electric field and voltage is a scalar. This is a capital V, and I'm sorry because we're going to have velocities and we're also going to have volumes, and there's just going to be a billion V's everywhere. It's something we have to deal with. But the reason why we're going to care about voltage, this other word for voltage is called potential or electric potential. And notice it's never called electric potential energy because electric potential and electric potential energy, sometimes called UE, sometimes just called U, they're related in that same way that force and electric field were related, where you just multiplied by a charge by this Phys2 quantity to get back to the Phys1 quantity we actually cared about. So this potential doesn't become potential energy until you have a second charge that you're dealing with. And so if we were dealing with, for instance, just the voltage due to a point charge, it looks like KQ over R. This is a good point for me to revisit that, hey, what were the units on this K? Now that we have this formula of KQQ over R squared equals force, well, I can say a Newton is equal to a whatever the units of K are times Coulomb squared. I've got 2 coulombs in the numerator divided by meter squared. So then I can multiply my meter squared over, and I can divide my Coulomb squared over. Great. These are the units for K. That's why I don't remember them. They're kind of funky. They're kind of weird. And it doesn't reduce to anything special. It's just kind of what they are. That's why I always say, just do the problem in SI. Just always convert everything to SI up front, always. And then you can know that you can use this fun little number here, which we'll also have another representation for later. If in case this is hard to remember, there's another way to remember it as well. But when we look at this piece here, you have to take the voltage made by one charge. So let's say we have the voltage made by 2. That would be this. And then I would do the charge 1. If I multiply Q1 in here, and I know the distance between them, now suddenly I know the potential energy held between 1 and 2. And note that you get the exact same answer if I just flip these pieces, right? If I said that this was V1 and Q1 right there, and then I just multiplied Q2 in here, I get the exact same answer. So this is one of those great parts about scalars, is that they're really, really easy to work with. But we have to keep in mind here that when we switch those pieces at the force level, we got the third law pair. When you get switching the pieces here, you actually get the same answer. So if you're trying to figure out what, if I say I had 1 and 2 and 3 charges, and I wanted to know the total potential energy in this configuration, you'd have to take all of these combinations and say, I have these 2 pieces, and I've got these 2 pieces, and I've got these 2 pieces. There should only be 3 terms. But because there are 6 ways you could combine these things, I could do 1 and 3 or 3 and 1, and those give you the same thing. If we had a similar adding rule to find what is the total energy in a configuration, if I add it up, each charge times the other charge, so I'm summing twice essentially, divided by the distance between those two, I would get double the answer I'm looking for, so I'd have to half it this way. We'll talk more about this when it gets into practice, but this is also going to be a good reason why I'm going to reintroduce something called a system schema, which some of you may have heard of if you've taken my class or somebody who I have similarly poisoned with good pedagogy. We'll talk about all of those pieces going forward. The big thing that I really want to iterate here is the similarity and structure between how we calculate the voltages and the E fields, where if I wanted to know the voltage of more than just a single point charge, I would have to say, well, the voltage is going to be found by adding up each charge that is in that distribution multiplied by K divided by each R. And that's it. It's much more simple to do this because adding up scalars is way easier than adding up vectors. We don't have to worry about all those magnitudes and directions not necessarily mixing appropriately. And then if I knew that this was the voltage made by a distribution, and I wanted to know the potential energy between some charge and that distribution, it's really easy. All I have to do is multiply this charge in, and I have it. I have the total potential energy stored in that distribution, or at least because of the addition of this. There will also be some intrinsic potential energy associated with the distribution itself, and we'll talk about that more, especially when we get to capacitance. And then similarly, if I had a countable number of charges, I could use this sort of formula. But if I had an uncountably infinite, a huge, enormous amount, if I had a mole of charges, and it's not worth counting over all of them, that's where we started saying, let's add up. Instead of adding up each charge over its distance, we would add up each charge divided by its distance, and then, of course, multiplied by this Coulomb constant to make the units work out in the measurement systems that we're dealing with. And then, of course, I can multiply in by this other external charge if I wanted to know the total potential energy. But typically, we kind of separate these pieces out because this is a lot to swallow, and we have to learn those practices before we then apply them. We have to learn those kinds of pieces. So, getting into that, some of these methods eventually fail us, where there's complicated geometries that are really hard to deal with. And by complicated, I mean something that looks so simple and innocent, where it's this highly symmetric, just lovely little sphere of charge. But if you tried to break the sphere into one little chunk here, and a little chunk here, and a little chunk like over here, suddenly this becomes this enormous, very bad Calc 3 problem that even if we can do, it becomes really hard to do, where we're trying to do this triple integral, adding up all these dq's over these horrible r hat vectors divided by these horrible r squareds, and the constant is about the only thing that makes this easy if we were, for instance, trying to calculate the electric field. And the voltage field is pretty similar, still bad in its own ways. We keep saying, you know, there's got to be a better way. And that's where we introduce this thing that we call Gauss's law, which in highly symmetric situations lets us exploit this new tool that we call flux. And so what this idea of flux is it's this idea of a vector flow. It says how much vector flows through some surface that we draw. So the idea here is that if I add up over two integrals, because I have to add up over an area, and I'm adding up how much of the E field actually goes through. This is what we would call electric flux. So we use a capital Phi and a lowercase e to represent this idea of electric flux. And the visualization here is if I had this sphere here that is emanating this electric field kind of outward everywhere, and I were to draw in some imaginary surface outside of this, and I break it into these itty-bitty chunks of area, and I define the area vector as perpendicular to those pieces, When we do this dot product here to say, hey, we only care about the parts of the E field that actually go through the surface. In highly symmetric cases, we're able to actually reduce this quite a bit. In this case, and details that I'll show much more thoroughly later, we eventually reduce this into something that looks like the electric field times the area. And then that area is really this area that we call 4 pi r squared, that area of the sphere that I have drawn here. And the thing that makes Gauss's law is when you specifically choose a surface that's closed. That's why we add in this piece. So this is no longer specifically just flux. It is still a flux integral, but it's a very specific flux integral. Gauss's law says that when you have the electric flux through a closed surface, it has to be equal to the charge you enclose divided by epsilon naught. And this is kind of just like a logic game where if I draw this bubble and I have some charge here and I compare it with a charge over here, the electric field line that goes through the area here enters, but then it leaves. And when it enters, that's negative flux. And when it leaves, that's positive flux. Depending on sign conventions, that's typically the convention we use in physics. Versus here, every line only interacts once, where it goes out, or in the case here, it would leave, enter, and then leave again. And so this net result is that you only get additions to this possible flux based on how much charge was trapped. And in this case, if I just had some total point charge plus Q, I'll call it, I would trap all of it. 100% of that charge is inside of that sphere I drew. And if I divide this over, I get this expression for the magnitude of the E field. Notice it's not a vector anymore because of when we did this dot product. And again, we'll talk about that in more detail when we eventually get there. This is going to be equal to Q over 4 pi epsilon naught times r squared, which looks suspiciously similar to, if I can draw a good epsilon, it looks suspiciously similar to KQ over r squared. And that's because this other expression that I promised, K, is equal to 1 over 4 pi times epsilon naught. Epsilon naught is this more fundamental constant to the universe, this so-called electric permittivity. Electric permittivity. And it will be a similar constant for magnetism called magnetic. Good. It's electric versus magnetic. Great. And then it's permeability for some reason. I don't know why I think it's intentional that we use two similar but different words for these pieces. But that's why I try to always pair them with the electric permittivity of free space for epsilon naught and the magnetic permeability of free space mu naught. E for electricity, M for magnetism, but Greek because we ran out of letters, I guess. The idea here is that we can conceptually have a reason why we have this experimental model matches a very robust, like geometric, intuitive theory. And each of those different approaches then has different useful applications depending on the type of problem that we are looking at. And then from there, we get an additional definition for voltage that is independent of where this came from. Like, where did this KQ over R come from in the first place? We got a really robust reason here why it came from here. The robust reason for why the voltage looks like our, where I have it, the KQ over R, is actually by definition, because just like we had an equation that went back and forth this way, there's actually an equation that goes back and forth this way. How force and potential energy were related back in Phys1 was by an integral. We said if I integrate the force along some path and I take a negative of it because of work energy theorem, I get the change in the potential energy. And if I set the potential energy to some reference as 0 originally, that's where we drop the delta. And it becomes the actual potential energy. And if I did the exact same thing on this right-hand side, where I said, if I integrate this Q times the E, dotted with a DL, and multiply a negative on it, I would get a change in voltage times that same charge, but that charge is just a constant, and it can divide out. And it's really just this fundamental relationship, this work-energy theorem-like relationship that relates these two ideas between each other. And when we couple all of these ideas together in some combination, it'll help us solve different problems, different situations, different scenarios, and gain more insight about how the universe works. That's really a lot of what we'll be doing in this class. I think the last piece that I want to do in this brief overview that will take us through the overview of Unit 1, and then I'll talk about like what units there are to remain and do a similar video for each of those other units. And then we'll get into the full gory details of everything. High satellite view, and then we zoom in, and then we practice each of those zoom ins in classes is sort of the idea, the strategy, the structure of this course. So the last piece that I want to talk about is that thing that I promised earlier, this thing that I called capacitance that had this units of so-called farads, which is short for Faraday, Michael Faraday, one of the people that did a lot of this early work in electricity and magnetism. And this idea is that it's rare that we have two charges alone. We often have these configurations that are often looking like these parallel plates, so just like two sheets of metal that are held really close to each other, like a distance d apart, and each of them has their own area A. And so when we're looking at these pieces, if we wanted to have sort of a better way, sorry, there's some notification that popped up and it's screwing up how my pen works. There we go. I can now figure out this new idea that we call capacitance, where we say this capacitance, we're going to define it as so-called Q per V, charge per volt. It's this ratio of how much charge can we hold divided by a voltage, but it's not really equal to charge over voltage. Like it doesn't depend on, it's defined by these pieces, but it neither depends on Q nor V. This is the equation we use to find it, but it's neither a function of charge nor voltage. And why is that the case? Well, what we do is we say, let's say that I have some charge here. I'm then going to use Gauss's law in some configuration. So in this case, we'll learn why eventually we draw this like cylinder thing. And we use that cylinder to find what's the electric field made by, if I put a positive charge over here, and later I put a negative charge over here, I'll do the same thing over here. I'll find what the electric field made by this thing is. And then I know the net E field made by these pieces. Then I use that electric field and I integrate that electric field over the distance as I travel from one plate to another. And that's going to give me the change in voltage. This is defined as a positive number. So when we're doing capacitance, we're often fast and loose with the rules of math and just like make it positive at the end. But we'll practice all of those pieces as we go. And then at some level, since this Q was, well, it's Q. Q is defined by itself. But this voltage, which is defined by the E field, which is defined by the Q, at some level, there's going to be a Q in here and it cancels out. And at the end, you're left with only geometric factors. In the case of a parallel plate capacitor, we get epsilon naught times area over D. That if I have a bigger area, I'm able to hold more charge for a given voltage. And if I have a smaller distance, I'm also able to hold more charge for a given voltage. But a bigger distance makes it harder to hold particular charge. I have a bigger voltage for the amount of charge that I'm holding. And so it's this geometric ratio, and it's dependent on some of these other pieces. And again, since K had units of newtons meters squared per coulomb squared, I think that's what it was. I don't remember. I always have to double check / rederive it. Great. And since epsilon naught and K were related to each other by K being 1 over 4 pi epsilon naught just has the flip-flop units of this. So a coulomb squared per newton meter squared times meters squared from our area, hey, at least those cancel, divided by meter. So a coulomb squared per newton meter is apparently the same thing as a farad. Doesn't really mean anything to us yet, and in a similar way that a coulomb, 1 coulomb of charge was a huge amount of charge, that means that 1 farad is a super huge, right? If you had 1 squared, essentially, I know it feels weird to square ones, but when you're comparing orders of magnitude of how many charges itself, if it was like 10 to the 19th or 10 to the negative 19th was the order of magnitude for a single charge, if you flip that 1 over, that would be how many individual charges are required to make 1 coulomb. That many charges squared would be required to make 1 farad. So 1 farad is a huge, like if you had 1 farad, a 1 farad capacitor, it's like the size of a water bottle. It's pretty big. So we'll keep some of those pieces in mind. Again, the last pieces that I wanted to do in this video for this quick satellite overview of everything. We've gotten sort of electric properties of materials, of individual charges. We've done some of the basics with electrostatics of how these charges are going to interact. But then we want to let some of those charges move in controlled configurations. And that's when we get into this idea of circuits. And as we start letting those circuits move, the charges move, we start realizing there's more we're not accounting for. There's sort of these fun, strange interactions because when you have moving charges, they actually create magnetic fields. So then we have to replace that, repeat that same kind of process we did in electrostatics with, well, now let's talk about so-called magnetostatics, which is just a statics course taught by Magneto, obviously. It's sort of this idea that as things move in a controlled and stable configuration, what magnetic properties manifest. So we'll talk about those sorts of things. What are magnetic fields? Where are they coming from? Static magnetic fields versus magnetic fields created by currents. And then we start slowly letting things slightly change a little bit within that as we get into things like Faraday's law. And that's when we really get to zoom back into the memes about this course. Like, what is this course really about? It's about the so-called Maxwell equations, which I'm going to write in two forms. I'm going to write them in the differential form, where if we take this symbol called the gradient, this del derivative, and I do different kinds of derivatives with these. So I'm going to take the divergence of an electric field, the divergence of a magnetic field, which is B field, which is if you have a stuffy nose and you clog your nose and you just say magnetism. That's sadly better than the real reason why we use B for magnetic field. So I'm going to stick with it. We have these four equations that tell us basically like the sources of E fields that come out from each other are because of charge densities. And this secretly turned into, and it's called Gauss's law, it secretly turns into the same thing we call Gauss's law in the integral form. And we'll talk about how they get in here. The integral form is going to be the one that's more useful to us, but the differential form is sort of this more fundamental thing, and it's how I remember them, so I have to use it. There are no sources of magnetic divergence that would require there to be a magnetic monopole, which we think there should be. Looking at symmetry in all of these equations, we're like, there should be one, there should be one. We just haven't found any, but if you find one, you get a cool Nobel Prize. Curly E fields. So this is how we break up fields into how they come apart from single points or how they go towards single points, and how they twist around points. And so twisty electric fields are caused by if you have a magnetic field that changes with time. Notice this is a different type of derivative. This is the partial with respect to time. And there's a negative here, which is so famous it gets its own name. It's called Lenz's law. This first one is called Gauss's law. This one awkwardly has no name because it's profoundly useless to us, but it's sometimes called like Gauss's law for magnetism. This one is called Faraday's law, and this minus sign is called Lenz's law, Lenz''S. It basically tells you about the sign, direction, relative orientation of these pieces. We'll talk more about that in much more detail later. And then over here, this one is the most interesting story, that what we call Ampere's law. Ampere's law is very French. You have to remember this grave accent, as my sister, who's a French major, tells me. It's going to be equal to this magnetic permeability constant times the so-called current density. But then there's this extra term that we found that also says there's another source of this, that it's mu naught times this thing that we call the displacement current density. And the displacement current is actually epsilon naught times how quickly the electric field changes. And so at the very end, the very last unit we get into is if changing electric fields create changing magnetic fields, create changing electric fields, create changing magnetic fields, it's this infinite chain that propagates forever, even if you have literally no matter. If you have no charge density and you have no charge movement, therefore, this equations still have to be held true. And that leads us into these propagations of waves. These electric and magnetic fields kind of wave in and out of each other and create these electromagnetic waves. And it finds out that when we do that wave math, we find the propagation speed as a part of that wave equation. And that wave speed happens to be exactly the speed of light. And that sort of is the definitive nail in the coffin for us figuring out that light is actually just an electromagnetic traveling wave. And that's pretty neat. And we'll shed some light on a whole bunch of different kinds of discussions. But again, the pieces that we'll end up seeing will be the integral forms of these, and the integral forms of these get kind of nastier. I'll write the Ampere's law one, the B dotted with a DL equals mu naught times I through, and then plus a similar term for the displacement current term. And the reason I'm highlighting this is to highlight also the necessity of Calc 3 pieces in this class. That this, how we came from here to here, is by using divergence theorem and the divergence operator. And I don't know why it's not called curl theorem, but Stokes's theorem. We use Stokes's theorem to go from here and here. And we will kind of use symmetry to avoid doing the full nastiness, and it will limit the situations that we can look at, and we'll learn other tools like the Coulomb's law kind of approach, and there will be a similar kind of approach for magnetism. But that's kind of this very high level picture of, I guess the last thing I should say within waves and optics stuff is that's where we get into all of the different phenomenon about, how do rainbows work and how do mirages work and mirrors and anything like that. And depending on how fast we get in the semester might dictate how much of that content we cover. The first 3 units are definitely the most important for Phys2. And then it's kind of just fun victory laps where the math is often easier, but the concepts are often a little bit wonkier within waves pieces. But that's sort of the roadmap for where we're going. Hope this info dump is or was or will be helpful to you. And I look forward to a great semester with everybody. Bye.